Welcome to Binary Bytes and Bitwise Operators in Python. My name is Chris, and I will be your guide. This course introduces you to binary number concepts and how you can use them in the Python programming language. In particular, you'll learn about binary numbers, bitwise math and truth tables, number representations, fixed and arbitrary precision integers in Python, bitwise operators in Python, frequent use of binary and bitwise operations, big endian and little endian byte orders, and overloading bitwise operators. A quick note about versions. The code in this course was tested using Python 3.9. Nothing is very version specific, but f-strings are used in some places. F-strings were introduced in Python 3.6, so to follow the code along exactly, you'll need at least Python 3.6. Everything is digital these days. At the time of this recording, I'm shopping for a new washing machine. It is pretty much impossible to find one with a mechanical control anymore. The retailers keep telling me how great it is that it can talk to my phone via Bluetooth. Until my phone figures out how to do my laundry, I'm not sure why this is important, but it does underline the fact that computer processors are everywhere. CPUs in computers are built on transistors, which are tiny components that act like switches. Every piece of data in your computer is represented through a series of these switches with the patterns of on and off forming a binary number. The ones and zeros in the binary number correspond to the on and off states of these switches. These binary numbers are then mapped to represent your data, such as going through a numeric transform to translate binary to decimal, doing a code lookup to translate binary to a character, or directly influencing the state of hardware in your system. Python isn't the easiest choice for manipulating raw binary data. It has lots of tools that can help you out, but some of the high-level language features that make it easier to code other things can make dealing with binary a bit more of a challenge. In grade school, you learned simple math operations like addition and multiplication. With binary data, you can do these operations as well as some others. There is a family of binary operators that are called bitwise operations. Each of these operations either combines two binary values into a third or manipulates the bits in a binary value. Most of the operations can be thought of as a series of steps performed on the bits within the binary number. The first bitwise operator I'm going to talk about is AND. AND combines two binary numbers, comparing the corresponding bits in each. If the corresponding bits are both 1 in the numbers being combined, then the bit is 1 in the result. OR also combines two binary numbers. This time, the bits in the resulting number are 1 if the corresponding bits are 1 in either of the operands. XOR is short for exclusive OR. It is like OR, but the bits are on only if the bit is on in exactly one of the operands. If both operands have a bit value of 1, the result will have a value of 0. Everything up until here has combined two operands. The next three operate on a single value. Not, also known as negation or inversion, flips the state of all the bits in the number. All the ones become 0 and vice versa. This is the left shift. All the bits in the result are the operand's value shifted to the left by n positions. The new bits pushed in on the right-hand side have a value of 0. Corresponding to the left shift is a right shift, moving the bits to the right instead of the left. Using bitwise operators, you can create and manipulate flags, access a portion of a number, or manipulate raw binary data. Next up, I'll dive into binary numbers. The zeros aren't so bad, but if you land on a 1, it's a bit pointy. Thanks. Tip your waitress. I'll be here all week. In the previous lesson, I gave an overview of the course. In this lesson, I'll be covering binary numbers. Computers are, well, everywhere. At the heart of all the digital goodness in our lives is one or more microprocessors. Inside a microprocessor, there are millions to billions of transistors. The funky collection of lines on the right is the circuit diagram symbol for a transistor. When an electrical charge is applied to the transistor's base, current can flow through the transistor between the collector and the emitter. Turn the charge off, and the current stops flowing. Transistors are small switches. Apply a charge, and the switch is on. Remove the charge, and the switch is off. By changing the charge to different values on a series of switches, you can form a pattern. Switches that are on represent 1, switches that are off represent 0. These patterns can be used to represent other things. The pattern 101 means the number 5. This particular mapping is based on a mathematical transform. I'll explain more about that later. The patterns can mean other things as well. Pi gets approximated by a 16-digit floating point number, which is represented by the following binary code. This code is actually comprised of 3 numbers, a sign indicator, and an exponent value, and a fractional decimal value. The letter A is ASCII 97 in decimal, which in the CPU is represented by this binary value. Even Mona Lisa's sly smile on your screen is really just a large array of these numbers. Each pixel in the picture is represented by a number. This drab-looking square of greenish is the hexadecimal number 7F8053. The hex number breaks down into 3 parts: the red, green, and blue that make up the color. 7F8053 is decimal 8,355,923, or this long string of binary digits. It's binary all the way down. So what is this binary number stuff? Let's take a quick detour and think about the numbers you probably know a little better. Decimal. Consider 4,239. This number can be broken down into 4 parts. 4,000 plus 200 plus 30 plus 9. Each of these numbers can be thought of as the combination of a number and a power of 10, with 1,000 being 10 to the 3, 100 being 10 squared, 10 being, 10, and the ones digit being 10 to the 0. Although base 10 feels right or special to us, that's just because it is what was taught to us at a young age. There's an argument that base 10 really only exists because of the number of fingers we have. Historical civilizations have used different bases. The Babylonians used base 60, while the Mayans employed 2 different bases, base 20 and base 360, depending on whether you were a priest or not. Those might seem kind of crazy, but they actually make math with numbers like 12 easier. How many hours on a clock? How many degrees in a circle? Yep, you're using more than just base 10 yourself. You're just not necessarily conscious of it. A number can have any integer base. Commonly in mathematics, the subscript here indicates the base. 4,239 base 10 is subscript 10. 4,239 base n has subscript n. For the general case of base n, each digit is a power of n. 4,239 base n is 4 times n cubed plus 2 times n squared plus 3 times n plus 9 times n to the 0. Note that no digit in a base n number can be larger than n itself. In base 10, each digit must be less than 10. Back to those switches, that on and off stuff, binary numbers, or base 2. Just like base 10 or base n, each digit is a power, in this case of 2. The number 1011 in binary is 1 times 2 cubed plus 0 times 2 squared, still 0, plus 1 times 2, plus 1 times 2 to the 0. This gives you 8 plus 2 plus 1 in base 10, for a total of 11 in base 10. In computer science, there are 4 bases that are commonly used. Decimal, because that's what humans are used to. Binary, because that's what the machines want. And the last 2 are things that translate back and forth to binary easily. Octal, which is base 8, and hex, or hexadecimal, which is base 16. Both octal and hex map to binary values, and with a bit of practice, you can convert them in your head. 5 in decimal is 4 plus 1, giving 0101 in binary. 2 squared plus 1. Octal, or base 8, allows for digits to be up to and including 7, so decimal 5 is also 5 octal. Hex, or base 16, allows for digits up to 15 in decimal, so one more time, the answer is also 5. Let's try another one. 8 in decimal is 2 cubed, so the fourth bit is on. 8 decimal is bigger than the maximum value of a digit of 7 in octal. So just like the other bases, you add a digit and roll the counter over. Or, going the math route, 10 octal is 1 times 8 to the first power plus 0. In hex land, you're still under 15. So far, the conversion from decimal to hex is pretty simple. It will get worse, I promise. Let's add one more to our 8 and get 9. I didn't even have to use my fingers. Adding 1 in decimal means adding one more in binary as well, so the first bit position increments. Adding one more to the octal value, so the digit goes up by 1. And good old hex still isn't complicated. It's coming, wait for it. This time I'll add 2 more to the decimal value, and that means incrementing the binary value by 2. That's a power of 2, so in this case, just turn on the second position. 2 more to the octal case still hasn't exceeded the max digit, so 1 octal becomes 13 octal. Notice that I don't call these 11 and 13. 11 and 13 are decimal concepts. For clarity, I will try to remember to keep using the digit style. This is the technically correct style, but most people won't want to be corrected if they use the incorrect style. You will hear people say things like 13 octal. All right, hexadecimal is base 16. That means the largest digit can be the equivalent of 15. How do you represent 15 as a single digit? You switch to the alphabet. 10 decimal is A in hex. 11 decimal is B in hex. That goes all the way up to 15, which is F. Last one, let's do something a bit bigger. This time I'm going to start on the right-hand side with the hex value. B5. Remember that B is 11 decimal, so this is 11 times 16, because this is base 16, plus 5. This turns into 265 in octal, and 10110101 in binary. I've grouped the binary number into 2 sets of 4 digits. This is done on purpose. Each of these 4 digits directly corresponds to a digit in hex. This is why hex gets used. It is a convenient short form for binary. 1011 is decimal 11, or B, in hex, and 0101 is 5 in both decimal and hex. If you have the binary equivalents of the 16 digits of hex memorized, you can quickly substitute one value for another. Fun fact, and this is the problem with my sense of humor, you're never going to believe what I'm about to say is true. Half a byte, that's 4 bits, or a single hex digit, is called a nibble. Who says computer people can't be fun at parties? And of course, in the more human-readable format, 11 decimal times 16 plus 5 is 181 decimal. Now that you've got binary in your brain, next up, I'll show you bitwise operations that affect binary values. In the previous lesson, I showed you the ons and offs of binary numbers. In this lesson, I'll be talking about operations on binary values. Bitwise operations affect one or more bits in a binary value. The most common bitwise operations are AND, OR, XOR, NOT, and shifts. Bitwise AND, noted as a single ampersand in most programming languages, combines 2 binary values into a result. Each bit in the values being combined is compared. If they're both 0, the resulting value is 0. If either of them is 1, then the resulting value is still 0. And if they're both 1, the result is 1. Bitwise operations can be expressed using something called a truth table. The header row and header column contain the values of bits being compared, and their intersection in the table shows the result. So, 0, 0 in the blue meet to form 0 in the gray. 1, 1 in the blue meet to form 1 in the gray, and the mixed values in between. Consider the following example: 1, 0, 0, 1, 1, 1, 0, 0, ANDed with 0, 0, 1, 1, 0, 1, 0, 0. Line up the ones, and any position with a 1 in both values results in a 1. Everything else results in a 0. Bitwise OR, noted as a single pipe symbol in most programming languages, combines two binary values. Each bit is compared, and if either of them is on, the resulting value has the corresponding bit on. 0 or 0 is 0, 1 or 0 is 1, 0 or 1 is 1, and 1 or 1 is also 1. Here's the corresponding truth table. And using the same numbers from before, anywhere there is a 1 in either number results in a 1 in the outcome. Bitwise XOR, also known as exclusive OR, is usually a caret in most programming languages. Exclusive OR is like bitwise OR, except both values being 1 results in 0. Only one of the bits can be on exclusively. 0 XOR 0 is 0. 1 XOR 0 is 1. 0 XOR 1 is 1. And the exclusive part, 1 XOR 1, is 0. Here's the corresponding truth table and an example. Follow the ones, but only if they cross a 0. There's the result. Up until now, all the bitwise operations you've seen have operated on two values. The NOT is different. It is a unary operation. Bitwise NOT is usually the tilde symbol in most programming languages and is responsible for inverting each bit in a binary number. So 0 becomes 1, and 1 becomes 0. Going through an example, everything flips to the other case. There are two bitwise shift operators, one for shifting left and one for shifting right. These are usually denoted as double less than and double greater than in most programming languages. Each shift operation includes a parameter, a number that indicates how many positions the bits are going to shift. The following examples are a bit messy, as they combine both binary and decimal numbers. Note the subscript next to each number. Subscript 2 means binary, or base 2, while subscript 10 means decimal, or base 10. 1 shifted left by 1 position gives 1, 0 binary, decimal 2. 1 shifted by 2 positions gives 1, 0, 0 binary, or decimal 4. Note that the new digits shifted into the lowest positions are all zeros. 1, 0, 0 shifted right by 1 position gives 1, 0. The rightmost digit of the original is chopped off. 1, 0, 0 shifted right by 2 positions gives 1. Because each digit in binary represents a power of 2, shifting left and right are the equivalent of multiplying and dividing by 2. This is like multiplying and dividing by 10 in decimal. Just add or remove a digit. 0 shifted left is still 0, and likewise 0 shifted right is also still 0. Here's a trusty example. With a left shift, digits move left, and zeros come in on the right-hand side. And now here's the right shift. The rightmost digits get chopped off. So far, everything I've been talking about is theory. As is often the case, practice is a bit messier than theory. Computers use binary values to represent numbers. The problem is, computers have limited space to store things, and that limitation has an effect on bitwise math. Consider an 8-digit binary number being stored in a place with enough space for 8 digits. What happens when you shift this left? Well, you can't put a 9-digit number in an 8-digit space. Complications ensue. This means bitwise manipulation of binary values may not have the effect you may think it does, depending on the programming language and the data type within the language that you're using. In theory land, everything so far has been an unsigned number, that means everything is zero or more, and all operations were logical, that means the bits are played with no consideration for what they are representing. These two assumptions are handled differently in different programming languages. Some languages even have the behavior change based on the data type being used. Did you notice the slide's title? If you're not familiar with the phrase, it's Latin for buyer beware. As a purveyor of the Python programming paradigm, you may find everything isn't peachy. Those two assumptions I just stated about Theoryland, neither of them apply to the practice of Python. Python's integer isn't unsigned, it can store negative values. The way the negative values are stored impacts the second assumption about bitwise logical operations as well. Next up, I'll show you how that last sentence I just uttered will make your life complicated.